Hey, hi guys, hope you're okay. It's Sunday and today I'm in good spirits. I found this really good place in Piccadilly in London um, that sells, well, very tasty kimchi. Right, well, what we're doing in this session is following on from previous video of interpreting a coefficient in a Cox proportional hazards model, and examples taken from the book Hosmer and Lemeshow. I'm not sure that I'm pronouncing that right. Looking at the first edition, chapter 4, and previously we were looking at the interpretation of qualitative explanatory variables. Otherwise, some people call them covariates. Um, and this time we're turning to the attention to interpretation of coefficients when we have a single continuous covariate in the Cox pH model. Right, so here's the data. So it's about, remember, it's about follow-up time of HIV positive individuals over a period. And what we have is censoring going on. So 1 indicates that an individual actually died at the recorded time, and if it's code 0, it means that the time that we have is just the time that last saw the patient alive, and that patient is probably, but we don't know the exact time of death, so that person could have died after the trial or could still be alive. Okay, what we notice is here that drug, whether you take drug on yes or no, historic in the past, and that is a qualitative variable, and that was an indicator variable. And last time we looked at the interpretation of this when it went into the model, and this time we're focusing our attention on age. Age is continuous. These numbers actually mean something as it's increasing. Obviously it means that the person's getting older and older. Right, so I want to fit the Cox pH model. Load the package survival. I've done it already, so I'm not going to do it now. And then, just like before, run the Cox pH using the command Cox pH, and now we're doing it on age. And I'm sticking to this method like in the book, the Breslow, although we know it's better to run the Efron, it's more exact. And if we can run the exact, if the exact works, it's better to run the exact, alright? But the exact for complicated models takes ages, takes forever, or it doesn't go at all, so that's why people tend to prefer then the Efron approximation. This Breslow approximation is not as good, but for some reason they're using it in the book, so let's just do that so the numbers match to what you see in the page of the books. Alright, and our focus is on the coefficient, and it's pretty much a breeze for when we have continuous covariates. So here you go. Just to recap, the exponential of the coefficient gives you the hazard ratio for in this case for an additional year increase in age. Age here is measured in years, right? The hazard ratio is just a word, but what does this number 1.08 tell us? Well, recall the kind of rule I told you about looking at this number. If the number is 1, that tells us that the risk of the event, in this case the event is death, the risk of death for a person who is 1 year older is the same as the risk of someone who's not 1 year older. I can say it more cleanly than that. So if that's 1, that's saying that the risk of death doesn't change for an additional year in age, and that is independent of the age at which the increase is calculated. So in other words, if a person is 20 going on to 21, if this was actually 1 and not 1.08, if the person was 20 compared to a person who's 21, the risk of death would be the same as if we compared a person who is 60 to a person who is 61, or compared to a person who is 90 compared to a person who's 91, right? So that's what I mean by saying that independent of age at which the increase is calculated. That phrase I'm just kind of repeating from the book, page 129. If this number here, this parameter, is bigger than 1, that the risk of death for an additional increase in age increases. If this figure is less than 1, that tells us that an additional year increase in age decreases. So first we've got to be able to get the right word. Is it increasing risk or decreasing risk or not changing risk? In this case, we can see that figure is above 1, or only slightly above 1, so we can say that for an additional year in age, the risk increases. And that's irrespective of the age at which the increase is calculated. Okay, so how much does it increase by? How much does the risk increase by an additional year in age? Increases by a factor of 1.08. Increasing by a factor of 1.08 is same as talking about an 8% increase. So what you do is you subtract 1 off the figure and multiply by 100 to convert into a percentage change. So if I did it here, just to, this is basically the formula. I take that figure, I subtract 1, and then I multiply that number by 100 to convert it into a percentage. So it's 8, so 8% increase. If that number turned out to be a negative, then we're talking about a percentage decrease. Okay, so we think to ourselves, well, that is plausible. We'd expect if the person gets older, the risk of death will increase. Now, once we've got the hazard ratio, we'd also like to report the confidence interval for that. So let's look at that. We can get the fuller output by typing summary of the object. Here you go. So we've got the original coefficients as before and something more. We've got the confidence intervals. So here you go. These confidence intervals, it's 95% confidence intervals, is respect of the hazard ratio, the exponential of the coefficient. Remember I told you, and I'll repeat again, that it can't be for this one, and it can't be for coefficient. So it can't be for coefficient, it cannot be for exponential of minus the coefficient figure, because for each of these guys, this figure does not fall in between these two. This does not fall in between this. Only this one falls in between this. So remember, an estimate and a confidence interval is similar. The estimate just gives you, it's like, what if I had to ask you what is your best guess of the hazard ratio, give me one number, you would say 1.085. But if I ask you, okay, don't give me an estimate, give me an interval, give me a lower value and an upper value where you think that traps the true hazard ratio, and with 95% confidence, whatever that means, you would say, oh, kind of very vaguely, I'm 95% sure that true value is trapped between 1.048 and 1.123. So can you see that they are saying similar things? So they should be consistent with one another. So to say that the true value lies between these two guys is consistent with this saying that the estimate is 1.08, because this guy is actually in this interval, isn't it? Whereas this guy's no way is that in the interval, because it's less than the lower limit. Likewise for the straight coefficient, that's way less than the lower limit as well, so it can't possibly be for those two, coefficient or the exponential minus the coefficient. And again, to revision, what's the interpretation of exponential of minus coefficient? We don't really need this figure. It's just looking at it the other way round. So it's talking about a person, if he goes not an additional year increase in age, additional year decrease in age. Additional year decrease in age leads to a factor change by 0.92, which is the same as saying an 8% decrease in the risk of death. Well, that's consistent with talking about it the other way around. 1 year increase leads to an 8% increase in death. Right, finally then, it says in the book here, let's just get it. I'm looking at first edition, page 127, bottom of the page. Bottom of the page. No, top of page 128. It says here, often a 1-year change in age is not of clinical interest. Physicians conducting the study may be more interested in 5-year change in age. In other words, 1 year might be too short a period. You might want to look at it in more medium term, like 2, 3, 4, 5, whatever. So what I want you to be able to do is to be able to calculate the hazard ratio and the corresponding confidence intervals for any amount of year change. See, the output given by R, and indeed for any kind of standard package, SAS, SPSS, Stata, it'll all look like this. It'll look very similar to what you've got on the screen here. But for any of those packages, how do I calculate the hazard ratio, i.e. this, for say a C year change in age and the corresponding confidence intervals? Alright, well, in this book, page 128, it shows you how to do it for 5 years. Right, I should be able to show you how to do it for any number of years. It's basically the same procedure. And for this, I've got the Excel spreadsheet here. You can do this by hand, but I'm using Excel spreadsheet. Okay, let's set it up. So what we've got is the estimate of the coefficient. Coefficient here, our beta being 0.0814. So let's put that in 0.0814. And the standard error of the beta, that is, let's move this aside, 0.01744. Is that right? Yeah. So let's type that, 0.01744. Take time to do this because one mistake and the whole calculation is wrong. Now the critical cutoff point for the 95% confidence interval, well, if the sample size is large, then this thing is we're going to use the normal table. So just off the top of your head, it's 1.96. This is from a standard normal table, Z table. Cutoff point for a 95% confidence interval. Okay, so the output here gives us the hazard ratio for a 1-year change. So I want to complete this. I've got a column here. Okay, okay. What we want to complete is this year change, and then I want the hazard ratio, lower limit of the 95% confidence interval, upper limit of the 95% confidence interval. And okay, let's just do 1-year change for now. This is the kind of the output that R gives you anyway. But let's just repeat. This is what you do. A year change, let's say it's a 1-year change, and remember the year change for the interpretation doesn't matter at what age it's calculated, which is a disadvantage in this model, obviously, yeah. But that's something you'll see can easily be rectified later on. What you want to do here is calculate the year change times the value of the beta. Okay, that. So let me just type it straight in. Like that. Okay. And then what you want to do, I need this figure, you see, but this figure is not reported in a table if you're going to report in a presentation. It's just for working. The hazard ratio would need the exponential, so type exponential, exponential. If you don't do it correctly, you'll see a little thing coming up, exponent number. Right, and then we enter the formula, and what we want, the hazard ratio, is this guy. Type that and enter. 1.0848. So that's pretty much what we got last time. Now the confidence interval, the lower limit first. The lower limit of a 95% confidence interval for the hazard ratio, that is equal to exponential, right? And what you do is the exponential of this guy here, the change times beta. So that's why you see I have a separate column. I don't want to type that in every single time, the formula for that. And then we do minus, and then this is where we need this cutoff value 1.96. 1.96 times, and then what we want is the change in the age, which is 1, times, and then we want the standard error. Okay. There's a proof for why this is the case, but we just want to know how to apply it at the moment, so let's just do that. That's 1.04835. Right, let's go to R. Okay, there you go. 1.048, right? Okay, so we get good. That means we're on the right lines, isn't it? 1.048, same number basically, two decimal places. Okay, then 95% confidence interval. The upper limit is going to be very similar, exponential, so if we do a minus instead of a plus. Yeah, let me not take any shortcuts. I'll just type it in slowly. Again, exponential, I'll repeat again. This year change times the beta. This time I'm adding and not subtracting 1.96, and then I multiply by the year change, 1, and then I multiply by the standard error, which is that figure. And okay, this time let's just click on it, because this is actually the short way to do it. And what you do, you put $sign in front of the letter E and in front of 3 as well, to stop it changing when I drag this down the column. Alright, 1.12. Yeah, okay. Well, I didn't think I'd seen that figure before. 1.123. Oh, 1.12. Yeah, round it up 3. Okay. Alright. Okay. So how about if I want 2, 3? Can you see this is what's so good about once I've set this up? I can do it for however many years. Of course, this trial, did it last 5 years or something? So it wouldn't make sense to continue on and on. But suppose I wanted to go on and on. Suppose I went up to 10 years. That's long enough, isn't it? Well, we don't know, but anyway, let's say 10 years. But I just want to show you that this is easily done. What you do, look, if you drag this down, let's just do it for this column, you'll see the numbers automatically update, because they'll know, they'll recognize the pattern that all you're doing is, let's see, that you're doing year change times the beta. So here should be D9, cell D9, yep, which is what it's saying, cell D9 times that figure, and all the way down. Alright, so indeed, if I grab the whole lot and I drag this all the way down, it'll give me, for all those years I presented there, why is it doing that? For all the years that I've got here, it'll give me the hazard ratio along with the lower limit and the upper limit. Now, why is that? E12, yes. Right, so when something like that happens, you just got to look at it. E12 minus 1.96 times D12, D12, okay, times E7, times E. Why has E7 appeared? Let's see. Times E3. Why didn't I put right, I needed to put $sign in front of standard error, because I don't want that. When you put a $sign, it means that when you drag down, those numbers that cell reference doesn't change. Obviously, I do not want the cell reference to change. So if I drag down now, so those numbers should be slightly off. Okay, does that look better? Alright, better check this as well. Alright, $sign in front of standard error, right, that's correct. Okay, that's why if you're not sure about that, just type in the actual number, and then it won't go wrong. Then it won't, yeah. Right, well, there you go. So I've got an entire table of hazard ratios, the confidence intervals for lower and upper limit. The one for the book is done for, it works out for you by hand, 5 year. So is this figure correct? I mean, does this agree with what they've got in the book? Let's just highlight this thing. Can I highlight this thing? What color shall I do it? Orange. Okay. Oh, it doesn't. Excel colors are not nice in Excel. All right. So what we've got is that the hazard ratio is 1.5. That's what it says in the book. Okay, 1.50. and the lower limit of the confidence of 1.264. Okay, yeah, it's about 26, slightly higher, right? And this one is 1.778, right? So the number pretty much agree. You might be asking me at this stage, how many decimal places should I report my number to? That's always a question that I get asked of students, whatever kind of stats class we're in. First of all, when you're doing your working, don't round, uh, don't round, um, don't round too early, right? So you try to keep several decimal places of accuracy. Only at the end do you um, do any kind of rounding. And obviously, in a presentation, it would not make sense to report it to how many decimal places are here, or I don't know, 6, 7, 8. It's meaningless. Those numbers are absolutely meaningless to so many decimal places far back. Since I told you that the hazard ratio could be interpreted as here 1.5 is like a 50% increase, so for that, it tells us basically for a 5-year increase in age, starting from whatever age you're looking at, leads to increase in risk by 50%. You see, so I've just done that, times that by 100 to get, well, take this figure minus 1 times by 100, that gives you your 50%. I don't say 50.23% because that's meaningless to people. 50%, you see. So you could think about the same thing with this one. So you might just have this to 1.27 because that would be talking about 27% as the lower limit, and 78% for the upper limit. See, so you might, in other words, 1.26 might suffice, or if you want to round it up, 1.27, and this one 1.78. All right. So I've rounded this up to 1.27 if I wanted to report it, because the third decimal place is a 6. It's bigger than 5, so I round up. If it was lower than 5, you round down. And if it's right in between, smack it on 5. It's up to you whether to round up or down, but be consistent. I do the same thing for this one. This one, 1.78231, I want to report it to 2 decimal places because that then I could say it's about 78% 78% increase. I would say 71.78 because the third decimal place here is 2. On a scale of 1 to 9, it's closer to 0, so I round down. Alright, that's what I mean by that. Okay, I just want to remind you, like in the book, that when I run this model, this is only for the purposes as an exercise to kind of interpret the coefficients. In this case, it's maybe it's the expected sign that we would would expect that the older you get, then it increases the risk of death. But whether or not this is true, it's probably not true. It's because the model is too simplistic, right? It doesn't capture other features that affect survival time. So that's a warning. And also, this Cox pH model relies on assumptions, and those assumptions have to be checked before we can actually go ahead and report these figures. Alright, but that's for another time. The next part is section 4.4, multiple covariate model. So that just takes this here model, but just adds on then more than one covariate. So that's for another time. Okay. Thanks for watching. Take care.